Hey Michael, so we're about to do a solvent extraction, but why are we actually doing a solvent extraction?
The objective of this experiment was to retain the entirety of the three solids through solvent extraction.
Okay, thanks Michael. So what solutes are we going to use?
So the solutes included are the 4-ethyl aminobenzoate, then benzoic acid, and the 9-fluoronone.
So those are some pretty cool solutes, Mike. But now to the solvents. What solvents are we?
So all the solvent extractions include diethyl ethers, but there's also one solvent for every solute. For the first solvent, we have HCl, and we have sodium hydroxide, and distilled water. Nice.
Alright Michael, so in the end, what were the results?
Well, they weren't what we were expecting. We had 102% of the benzoic acid.
Okay, not bad.
298% of the benzoic.
298%? That's almost 3 times what we expected. Oh well.
Well, mistakes happen, you know?
Fair enough.
And 88% of the 9-fluoronone.
Not too bad either.
We got 4 milliliters of diethyl ether and poured it into the vial containing the solutes. We put the vial onto the vortex mixer to dissolve all of the solutes. Then we put the vial in an ice bath to reduce possible unwanted reactions. Then we poured 2 milliliters of 3 molar HCl into the vial. We put the vial onto the vortex mixer to make sure the HCl dissolves all the ethyl 4-aminobenzoate. We put it to chill in some ice water, then extracted the bottom layer of HCl containing the solutes. The HCl dissolves the aminobenzoate because the HCl donates a proton to the amine group through an acid-base reaction. We put the HCl into a small Erlenmeyer flask. We added another 2 milliliters of HCl to the vial and repeated the process of extracting the bottom layer to get the remaining solutes out. We made a shallow ice bath to put the Erlenmeyer flask in. Then we added 6 molar of sodium hydroxide to neutralize the HCl through an acid-base reaction. We used a litmus paper to check if the HCl became a base, which is shown by it turning blue, revealing the pH of 11.
Perfect.
We put the flask back into the ice bath while we masked the filter paper so we can later check the yield of the extracted solute. We put the filter paper in a funnel and wetted it with distilled water to remove the air between the filter paper and the funnel. We poured the neutralized HCl into the filter paper and washed the flask with distilled water to get the remaining solutes out. We put the filter paper in the oven to evaporate the water. We kept it in the oven until the filter paper's mass didn't change significantly.
Oh, it didn't decrease.
We noticed the nasty yellow color, which shows the HCl somehow dissolved some of the fluoronone. This partially explains why we collected such a high yield, but it does not explain why we got 149 milligrams, 3 times the expected yield. We put some of the solute into a capillary tube to test its melting temperature. It melted at 87 degrees Celsius, which is around 4-aminobenzoate's melting point of 87 degrees Celsius.
After completing the first part of the experiment, 2 milliliters of 3 molar NaOH was added to the ether solution in the vial to neutralize the benzoic acid through an acid-base reaction in which the benzoic acid donates a hydrogen to the NaOH. This produces the benzoate ion, which goes to the aqueous layer that is separate from the rest of the ether. Again, we put the vial on the vortex mixer to dissolve all the solutes. We chilled the vial in an ice bath while the layers separated.
The ice stops unwanted reactions from occurring, like stasis freezes a game.
Next, we extracted the aqueous layer and put it in its second 10 milliliter Erlenmeyer flask.
We're getting an Oscar for this.
Next, we added 2 milliliters of 3 molar NaOH to the vial in order to collect as much benzoic acid as possible, because NaOH and benzoic acid will have an acid-base reaction together. The reaction is shown in the following picture. After briefly shaking the vial by hand, we put the vial in the centrifuge so the diethyl ether mixes with the 3 molar sodium hydroxide to dissolve the benzoic acid. Again, the aqueous solution was removed and added to the second Erlenmeyer flask. Next, 3 milliliters of 6 molar HCl was added to this Erlenmeyer flask to create an acid. This acid occurs because HCl donates a hydrogen to NaOH. Litmus paper was used to check that the solution became an acid. We knew the solution had become an acid when the litmus paper revealed a red shade corresponding to a low pH of around 1. We put the flask back in the ice bath. Next, we masked the filter paper so we could later check the yield of the extracted benzoic acid. This mass was 951 milligrams. We put the filter paper in a funnel and wetted it with distilled water to remove the air between the filter paper and the funnel. We poured the newly created acid onto the filter paper and washed the flask with distilled water to get out the remaining solutes. Water is a good cleanser because rinsing a solvent with an admissible solvent makes sure there is no leftover unwanted product. Rinsing ether with water is done to make sure that no water-soluble substances are left in it, such as salts. Additionally, benzoic acid and the water do not come in contact with each other for long, and benzoic acid is not very soluble in water, so most of the benzoic acid will not dissolve.
Oh yeah.
We put the filter paper in the oven to evaporate any remaining water. We kept it in the oven until the filter paper's mass did not decrease significantly. The resulting mass was 1,002 milligrams. When the filter paper's mass was subtracted from 1,002 milligrams, the resulting mass of the benzoic acid retained was 51 milligrams. The reason this number is 1 milligram above the initial mass of benzoic acid is because the resulting mass could have included grams of water that the filter paper was potentially still holding. This error contributed to a larger resulting mass. We put some of the solute in a capillary tube and put it in a melt temp to test melting temperature. It melted around 123.3 degrees Celsius, which is 1 degree Celsius off from benzoic acid's accepted melting point of 122.3 degrees Celsius. This inaccuracy could have resulted from 2 issues. First, the benzoic acid could have been contaminated with a compound with a higher melting point. Second, the melt temp heats up faster than the capillary tube inside it, so the melt temp's temperature reading could have been a degree higher than the actual temperature of the substance inside the capillary tube. However, since the melting point was only 1 degree Celsius off, this suggests that even with the previously discussed error, the product retained was mainly made up of pure benzoic acid.
We measured 1 milliliter of distilled water and added it to the remaining ether using a pipette. The water bonds to remaining unwanted solutes, like salts formed in the previous steps, and this purifies the solution when the water is removed. We put the vial on the vortex mixer to ensure that the ether and its solvents fully mixed with the water, and then we put the vial in a centrifuge to separate the layers well. We extracted the bottom water solute layer and added it to a small Erlenmeyer flask. We repeated the washing process again with another 1 milliliter of distilled water to ensure that there were no other leftover or unwanted products. The goal of this last part of the experiment is to isolate the ether and the 9-fluorinone in it, which are the neutral components that group together. After wetting the ether, we masked out 30.8 milligrams of sodium sulfate and added it to the ether. Sodium sulfate is a drying agent, so it will help remove any remaining water from the solution. We mixed it on the vortex mixer to ensure that the sodium sulfate bonded to all of the water, and after leaving the solution to dry, we extracted the ether using a syringe, careful not to collect any sodium sulfate, and added it to a tarred vial. Again, we added 1 milliliter of ether to the vial, mixed it with the vortex mixer, and extracted the ether. The repetition ensures that none of the original ether nor the solutes in it were left in the vial with the sodium sulfate. Then we dried the ether solution using a slow stream of nitrogen gas. This evaporates the ether but leaves the solutes. We put the vial in the hood to finish drying overnight. We remasked the vial the next day. However, the numbers seemed a little bit high, so we were suspicious that the solution was still wet. We dried it again with more nitrogen gas and remasked it. This time the mass of the vial with the solutes was 22.092 grams, and after subtracting the mass of the vial, the amount of 9-fluorinone was 44 milligrams, so we only lost 6 milligrams from the original 50, which was probably with the aforementioned HCl and 4-aminobenzoate. We melted the 9-fluorinone to confirm its identity, and the melting point found was 82 degrees Celsius, which was 2 degrees too low. However, since the other solutes had higher melting points, this slightly lowered melting point was probably due to human error in the melting process. Solvent extraction has many important applications. Unusable petrochemicals can be refined into valuable, pure petroleum. Solvent extraction allows for the production of ash-free coal, which is much better for the environment. Finally, solvent extraction is the most common method to isolate naturally occurring medicines from plants, like aspirin and digoxin.